So hi everyone, in the last part of the lecture I am discussing Carnot heat engine. We have discussed heat engine, we have calculated the efficiency of heat engine, and we have discussed how heat engine, what is the efficiency of a Carnot heat engine and why it is called to be a idealistic heat engine. So I have discussed in the just last part of the lecture that it is the engine that is having the highest theoretical efficiency. So this is the engine which is having highest theoretical efficiency, and this is that. Okay, so it is related to the efficiency of the efficiency is related to the temperature of the source and the sink. So we have discussed this why it is so ideal, because of this system, this piston cylinder system. If you see, the bottom wall is perfectly conducting, so that whatever the heat you want to supply to the system, it will go without any loss. The other walls are perfectly insulating, so there is no loss in that. The gas is also ideal in nature. The working fluid or the gas is ideal gas, and the piston is frictionless. Okay, so this is about the system, how it is there. So basically, when we discuss Carnot heat engine, the cycle of Carnot heat engine goes like this. So if you see a PV diagram, so in PV diagram it goes like this. So first it go from P1 V1 to P2 V2, that is isothermal expansion. Then we are having P3 V3, that is adiabatic expansion. Then we are having isothermal compression. That is P4 V4, and finally we are having adiabatic compression. So it goes like this. So in blues it is adiabatic process, and in blacks it is isothermal process. So in blue it is adiabatic process, and in black it is isothermal process. And when there is a isothermal expansion, so here temperature is T1, because it's isothermal process. Again temperature is T1 here. Then it is adiabatic process, so temperature will change, so it becomes T2. Again it is isothermal expansion, so temperature remains T2, and then it goes back to T1. So you have to keep this, or keep all of these things in mind. Now one by one we will look how this cycle is going and how the process is happening. Okay, so in the first part of the cycle, it is isothermal expansion. So in case of isothermal expansion, we are having a piston cylinder system. So consider this piston cylinder system as that idealistic that I have discussed. So I am not going to tell you again that which wall is conducting and which wall is insulating. I have already discussed it. I am taking that piston cylinder system only. Okay, so we are having this piston cylinder system, and we have connected it to a heat source. Maybe I can use another color. So we have connected it to the heat source. Another point I have to tell you is that the heat source that is at temperature T1. So the source has having infinite heat capacity. That means how much amount of heat is taken out from the source, it will not going to decrease its temperature. So no matter how much amount of heat is taken out from the source, it will not going to affect its temperature, and that is what we have infinite heat capacity. So the wall is thermally conducting. So you are giving heat to the system, and due to that heat there is a process happening where there is an expansion. So there is a expansion, and that expansion is because in order to maintain the temperature of the fluid which is at temperature T1, okay, so we want to maintain the temperature of the fluid T1, and therefore there is an expansion, that is isothermal expansion, and that is a slow process. Because process is slow and everything is there, that thermally conducting, thermally insulating walls are there, process is idealistic, it is reversible as well. So in Carnot heat engine it is reversible, the process is reversible as well. So this is isothermal expansion. So this is P1 P2 V2, but T1 remains T1 because it is isothermal. And there is expansion in order to maintain that temperature. Now in case of adiabatic expansion, next part of the cycle, that is adiabatic in case of adiabatic expansion, we have again taken, now we have after this expansion we have taken this, we have removed this source that is at temperature T1, and we have placed on some sort of a stand which is isothermal, such that there is which makes this wall insulating as well. Okay, now we have take this piston cylinder system from the source and put it over So keep this in mind that we are now at initial condition, that is P2 V2, and now it is connected to a, this is also become insulating, this wall is also become insulating. Now this wall is become insulating. There is an expansion because there is a change in temperature. So temperature is going to change. So it will go from P2 V2 to P3 V3. So there is a slow expansion going from P2 V2 to P3 V3, and temperature becomes T2. So it will go to so there is this expansion is happening as soon till it reaches to temperature T2. Okay, so there is a adiabatic expansion, and in this curve it looks like this. Okay, so I think I will make it separately. So we are having from here to here, and this is P2 V2 T1 to P2 P3 V3 and T2. So there is a slow expansion that is adiabatic in nature. So in order to maintain no heat exchange with the surroundings, the temperature will change, and that is because of the adiabatic expansion. Now in next cycle there is again isothermal compression. Okay, so in case of isothermal compression, we take this piston cylinder system and put it on a sink that is at temperature T2. Maybe fine. So we are having this the same piston cylinder system now at P3 V3 and T2, and sink is attached, which sink means it is trying to extract heat from this conducting wall. Okay, so there is a heat coming out from this conducting wall, and in order to balance the temperature, so this is sink, that is again with infinite heat capacity, which is maintained at temperature T2. So in order to maintain the piston cylinder system temperature at T2, there is a heat transfer between the, because it's a sink, it is extracting heat from the piston cylinder system, and due to that extraction of heat, there is a compression. Okay, so this will become this, and it will go to P4 V4, and temperature remains T2, and it will looks like this. So that is P3 V3 T2, and that is P4 V4 T2, and the last part of the cycle is, that is adiabatic compression. Now when you remove the sink, it tries to go back to its initial temperature, and due to that it can only possible when there is a adiabatic compression, because as soon as there is a compression, the temperature increases, and T2 the temperature of the system goes back to T2. So there is, now you remove this sink again and make the bottom wall insulated. Now we are at initially P4 V4 T2, and we have made this wall again insulating, but there is a transfer of heat. So there is no transfer of heat. So in order to but there is a adiabatic compression, that is because it wants to go back to T1 temperature, and T1 temperature, in order to go to T1 temperature it needs some compression, and so there is a compression is there. Therefore it will go back, P4 V4 go back to P1 V1 and T1. Okay, so this process will looks like this. P4 V4 T2 to P1 V1 T1. Okay, and altogether this process finally looks like this. Okay, so this is the final process. So I think we have discussed Carnot heat engine in detail, and this will going to give maximum heat efficiency, and the reason being is because it is idealistic in nature. We are saying perfectly conducting, perfectly insulating, frictionless piston cylinder system, and the sink and the source are having infinite heat capacity. So that is all going to make Carnot heat engine to be having highest theoretical efficiency. So in the next part of the lecture, I will be going to derive this efficiency, which we called as maximum efficiency, and we will look at each cycle again and find out the work done, and I will show you that net internal energy in the cyclic process is 0, and the net work done will give you this highest efficiency, and that is highest in nature. So I think we'll talk that about in the next part of the lecture. Thank you for your kind attention.